Okay, we're trying to create a neural network with an input node, a hidden node, and an output node. So far, in the previous videos, we've taken the input value, fed it through the hidden neuron, taken the output from the hidden neuron and fed it into the input of the output neuron. We've then calculated the resulting calculation of the neuron as a whole, compared it to our target value, and worked out the error function. So we're just trying to work out that if the question is 0.3, the answer is 0.6. So we've then subsequently worked out what the change we need to make to the weight 5 in order to make the error slightly smaller. And we did that by partially differentiating the three equations that weight 5 contributes into the error, which we did in the previous video to calculate this value here. And what we need to do now is similar, but not exactly the same, for the hidden neuron. So I'm going to copy these values in the hope that some of what we've already done proves useful, and see if we could work out how to calculate this value here. So to start with, this is the new value of weight 1. Anything else need to change? No, I think we're good. So let's start over here and let's try and work out what happens. Now we know what happens to this because we've typed it all in, but let's just recap. It goes into the summing function, it goes into the adds into the bias, we apply the sigmoid function, that gives us the output of the hidden node. That output of the hidden node gets fed into the summing function of the output node. That gets added to the bias. You can ignore these because these are just the calculations for the back propagation. It's over here we're kind of concentrating. That then gets fed into the output, which is the sigmoid function of the net value, and that gets fed back into here. So quite a few steps. Before we had 3 steps, now we've got 1, 2, 3, 4, 5 steps, I think. But let's just, before we dive in, let's just look at it from the other way around. So we do it the other way around. We'll take the error and look at the precedent. So that goes from there to there and to there. So again, ignore this. This is just the target value coming in, right? But we've already worked out these first 2 steps, right? We worked out that the gradient of that bit there is that, and the gradient of that bit there is that. So the gradient of those 2 as a whole still remains this delta. I knew that would come in useful. So that delta basically will get us back as far as this net output, right? Now from the before we went from the delta, which was from the net output, we worked out the weight 5. We had to take the output value because it's that comes in. Now we're in a slightly different position, right? It's not, firstly, it's not these values here that we want to start with. We want to start from here, which represents the gradient as far back as that. We then need to work out how we get this other bit over here. So it's how we get from the output of there into this one here. Right, so we'd already got as far as there with the delta. So now we need this line here. This line is G13 times K10, which is the output times weight 5. So we need to differentiate that with respect to the output. So that's the output times weight 5 plus the bias. We differentiate all that. The output of hidden 1 times weight 5 plus the bias. We differentiate that with respect to weight 5. The bias is a constant, so it goes, and we're differentiating with respect to weight 5, so that goes, and we end up with weight output 1. So effectively, what we're saying is that to get from there to there to there, we can use this delta, and then to get from there back to there, we've got OutH1. So if I take the OutH1 times the delta, it should get me back to this equivalent point here. So that means we need equals the delta times weight 5. So that will get me back to here. Okay, let's get rid of these arrows. So that's got me back as far as the output, right? Our next step is go from the output to the net. Well, that's the sigmoid function, which we've already calculated here. So that still stands. I knew there would be some reuse. Let's just change this. It's the output to the, not to the error, this is the output of hidden 1 to the sum of output 1. Doesn't quite fit in my cell, but I think it's okay. Let's just check that value again. So yes, that's weight 5 times the delta. So I'm going to keep the delta again here, in case that proves useful for reuse. It certainly did for before, because we were using that here. This delta H1, delta W1, right? Let's see. So we've got back as far as that maps that, that matches that step there. So this value, this delta gets us back as far as the net. So we need to just do the final step to see how W1's involved getting to here. So W1's involved in this calculation here. W1 is W1 plus times 0.3 plus the bias. So it's basically W1 times input 1 plus the bias. And I need to differentiate that with respect to the weight 1, because it's weight 1 I'm trying to work out the gradient for. So let's differentiate this with respect to weight 1. Well, plus b goes because it's a constant. Differentiating weight 1 with relation to that is W1 times I1 just gives me I1. So basically what I need to do is to take this delta and multiply it by I1. So let's do that. Oh, and good old Excel's done that for me, right? In the same way as we did this multiplication back to here, we've just got the same multiplication back to here. It's already included in my rate calculation. And let's see what that gives us. Okay, so we can just do the same thing as we did here. So we take equals weight 1 minus, get it right this time, this value here. So that gives us a value of minus 0.0079. Okay, so that then has differentiated the hidden node. Anything else we need to do? Just maybe we could put the word backward propagation there, and I think that'll do.